So here is a YouTube video talking us through the second worked example of, for problem 19, and this problem is located on page 389 in the back of your chapter 12. And the reason we're working through it is because the data are presented in a different kind of a way, and so that you can make sense out of it, because any ANOVA problems that you'll get either with the homework or practice exam or on the test may be one of the two different ways. You may have the raw scores to work with, and that was consistent with the way that we worked problem number 9 in the first YouTube video, or you may have the data organized like this one here in problem 19. Depending upon what data is or is not present, kind of governs how you work the formula worksheet. So I'm going to work through an example of both so that you have a way to be able to successfully do either kind of problem. So if you're taking a look at the way the data are laid out in problem 19, notice that again there's 3 treatments, and the total scores, which again that's synonymous. The capital T is just the total of all the scores in the treatment group, and it's consistent synonymous with sum of X. That's given to us, and so the total for total scores in treatment group number 1 is 16. For treatment group number 2 is 24. Treatment group number 3 is 32, with a grand total of 72. And then if you look down each of the columns for each treatment group, you'll notice that the little n's representing how many cases in each treatment group are provided, and they're different sizes. So treatment group number 1 had 8 scores in it. Treatment group number 2 had 6 scores, and for 3 it was 4 scores, for a total big N of 18. Now because we don't have the raw scores, we won't go through the process, can't go through the process of squaring each of those raw scores and then summing those up, but because we worked it in problem 19, hopefully you understand how that value of 464 that is given to you in the data set, sum of x squared of 464, where that comes from. And so you just need to enter that in on line 15 here. Now we do have the total values, the total scores for each treatment group, so just like in problem 19, we're able to calculate that component that's consistent with the sum of squares formula. So these series of steps is like the step in the sum of squares formula, sum of x in parentheses squared divided by the n of that treatment group. And that's what you see right here, where the total of the first treatment group was 16, so 16 squared gives us a 256, divided by the n of that group works out to 32. So we're able to do that for each of the treatment groups, and then you add those 3 values up, and that total is 384. So turning over the page, the second page, this is where we are able to enter in those 3 intermediate quantities. But one of the things that I've added this time around is the alternate way of how you calculate SS within and SS between. So if you work through or listen to the first YouTube video with problem 19, hopefully you kind of have a handle on how the intermediate quantities work to be able to calculate SS total, SS within, and SS between, subtracting one from the other. But there's going to be times when the data is presented to you that you may not have the t values given to you. You may just have the sum of squares given to you for each of the groups. Here we happen to have both, and so I seized the opportunity to show you that the alternate form of calculating SS within brings you the exact same results. So say that we didn't have the totals, and we weren't able to calculate the value that we would enter in on line number 23, that 384. Say that we just had each of the sum of squares for the however many treatment groups we had. Well, following the alternate way of calculating SS within, all you have to do, just like it specifies right here, is you just sum up the sum of squares for each of the treatment groups. And for treatment group number 1, the sum of squares is 40. treatment group number 2 it's 24, treatment group number 3 it's 16, and with a total, adding those up, it totals up to 80. Well, that's exactly what you would get if you were able to subtract the intermediate quantity 2 minus intermediate quantity 3. So either way will get you there. Again, it just depends upon the data that you have available. So notice that also there's 2 possible ways to calculate SS between. So if you had all the intermediate quantities available, then you would subtract one from the other, just like you learned in the first worked example. But if you didn't have intermediate 3, then you could still get there. You could still calculate SS between by subtracting your SS total of 176 minus the SS within that you calculated using the alternative method, and you would come up with 96, which is the exact same value depending upon whatever method you selected. So from there, it's the same process as you learned in the first worked example. You calculate your 3 degrees of freedom values, and then you you use the SS between, DF between, SS within, and DF within values to calculate your mean square values, your MS between and your MS within. And then finally, you put those MS between divided by the MS within numbers to work for you to come up with your F value. So that brings us down to the ANOVA table. And I started talking a little bit about the ANOVA table in the first worked example, but we'll talk a little bit more about it. It's a universal format, and in any research article summing up research where the researcher used an ANOVA as the test statistic, this would be the way that the data would be organized. And it's always laid out in the same format. Sometimes you see the word source right here above how the variability is partitioned. And the only alternative that you might see, alternative format, is sometimes the sum of squares column is listed first, sometimes the degrees of freedom column is listed second, but generally the format is laid out in the same universal fashion. And if you know how to read the table, then notice a couple of things that are important here. The columns should add up to the total. In other words, 2 plus 15 adds up to 17. Likewise, 96 and 80 adds up to 176. So if you're working an ANOVA using this worksheet and you get to this point and your between and within values don't add up to your total, that's a little clue that you probably made a math mistake in a previous step and to go back and to recheck your math. Also, notice that the rows work in a predictable, consistent way. The sum of squares divided by the degrees of freedom value, the DF value, is where the MS value comes from. So 96 divided by 2 gives us a 48. 80 divided by 15 gives us a 5.33. And then 48 divided by 5.33 gives us our F value. I know that you have a homework problem where you're going to be called upon to complete the ANOVA table, generate all the values that would go into the ANOVA table with just a few of the numbers. And if you know how the columns work and the rows work with respect to the columns add up to the total and the rows you can divide the SS value by the DF value and so forth, you can easily generate and complete all of the numbers in the ANOVA table. Now, this is the proper way to present the data once you've finished your ANOVA test, where you start out listing the test statistic first, and for ANOVA it's a capital F italicized, and then in parentheses the degrees of freedom. Now, the very first number is always DF between, okay, and the second number is always DF within. So that's where those two numbers come from. And the first number is associated with the numerator. The second number is associated with the denominator. Now, the reason that that's important is when you when you need to find the critical value to compare your FCalc to the F value that you calculated using your data. to the table value, the way the F table is set up is that there are columns associated with the numerator, all right, and there are rows associated with the denominator. So to find the proper critical value, you would orient on the numerator column and go to column that's listed under the value of 2, and then you would go down to row 15, and at the intersection of that column and row you find two possible values, two possible critical values. The bolded one, if you're doing an ANOVA test at an alpha of 0.01, then the bolded value is going to be your critical value. If you're doing your ANOVA test with an alpha of 0.05, then the unbolded value is the one that you would select, and that's where this one came from, 3.68. And from there, you just determine whether your F-calc is larger than your F-crit, and if it is, then you're able to reject the null hypothesis. And finally, the next step, there's a couple of next steps. If you have a statistically significant F-test, one of the customary things, two of the customary things to do are to do a measure of effect size, and for ANOVA it's called eta squared. Really, really easy to calculate. You just divide your SS between by your SS total, just like it's laid out here, and you get a value that is your measure of effect size. And the way that we interpret this is we transform the value into a percentage. So we're able to say that 55% of the variability amongst the scores can be attributed to the treatment effect, whatever that treatment effect was. And then we also would do post hoc tests. If you listen to my lecture on the PowerPoints, it gives you a little bit more information about both of these next steps. So hopefully walking through this problem will help you work the ANOVA worksheets a little bit better for all the problems that you encounter.